It's single speed from 0 to 200 miles an hour. So it's just, the RPM is so crazy that just the centrifugal force wants to expand the rotor. So the carbon overwrap actually holds the rotor, basically holds the rotor together. It's like madness.
There is a moment in engineering history when something arrives that does not simply improve what came before. It makes the entire conversation obsolete. The internal combustion engine did it. The transistor did it. And quietly, without fanfare proportional to what it actually meant. Tesla did it again with a motor small enough to lift with your bare hands. But before we talk about what Tesla built, we have to talk about what everyone in this industry believed was permanently, physically impossible, because that belief is what makes this story worth telling. For as long as electric vehicles have existed as a serious engineering pursuit, there has been a constraint that shaped every design decision every automaker ever made. It is not a business limitation. It is not a funding gap. It is physics, and physics does not negotiate. The constraint is this. Inside every electric motor, there is a spinning component called the rotor. The rotor is the mechanical heart of the system. It is what actually turns electrical energy into movement. And the faster a rotor spins, the more it becomes its own enemy. At high rotational speeds, the forces acting outward on the spinning mass become enormous. Engineers call this centrifugal force, and at the speeds required for serious performance, it does not merely stress the rotor. It wants to tear it apart from the inside. For decades, every motor designer on Earth accepted a simple consequence of this reality. There is a speed ceiling, and you build below it. You could push for more performance, but at some point the rotor would deform, weaken, and ultimately fail. The ceiling was real. It was enforced by fundamental physics, and the entire global automotive engineering community had quietly agreed to live inside it. This agreement was never written down. Nobody held a conference to formalize it. It simply existed as the invisible boundary within which every electric powertrain on the planet was designed. More power meant more heat, more weight, more cooling infrastructure, and a car that drank its battery in exchange for acceleration. More range meant backing off performance. You picked your compromise and engineered toward it. That was the deal. Tesla decided the deal was unacceptable. The answer Tesla's engineers landed on sounds almost absurdly simple once you hear it. They wrapped the rotor in carbon fiber. That sentence does not convey the difficulty of what it actually means. So let us slow down and look at it properly. Carbon fiber is one of the most remarkable materials human beings have ever produced. It is extraordinarily strong in tension, meaning it resists being pulled apart, and it is exceptionally light. Those two properties together make it ideal for a specific application, containing something that wants to expand outward under force. By wrapping the rotor in a precisely wound sleeve of carbon fiber, Tesla's engineers essentially gave the spinning core a cage, an external layer that squeezes inward against the very centrifugal force trying to fling the rotor apart. The wrap does not add much mass, but it adds an enormous amount of structural integrity at the exact location where integrity is needed most. In principle, this is elegant. In practice, executing it is one of the more punishing engineering problems imaginable. The fundamental challenge is thermal expansion. Carbon fiber and copper, the primary conducting material inside a motor rotor, respond to heat very differently. When the motor runs and temperatures rise, the two materials want to expand at different rates. This means the carbon wrap and the rotor it contains are effectively fighting each other the moment the motor warms up. A wrap that is too loose will fail to contain the rotor. A wrap that shifts under thermal cycling will eventually crack or delaminate. To survive, the carbon fiber must be wound at extreme tension, so tight and so precise that the resulting sleeve maintains its containment function across the full operating temperature range of the motor. No machine in existence could do this when Tesla decided it needed to be done. The tension required, and the uniformity of that tension across the entire wound surface, exceeded what any available winding equipment could achieve. So Tesla built the machine. This is the part of the story that deserves to be repeated slowly. Before Tesla could manufacture the rotor, It first had to design and build the specialized winding machine capable of producing it. The breakthrough product required a breakthrough manufacturing process that did not yet exist. So the company invented that process first, then used it to build the product. The result was a motor that spins at over 20,000 revolutions per minute. That number belongs to industrial turbomachinery, not to the vehicle that takes children to school on Tuesday mornings. At those rotational speeds, even a microscopic imbalance in the rotor, a flaw invisible to the naked eye, would not create a vibration problem. It would create a catastrophic mechanical failure. The carbon sleeve is not merely helping the motor perform better. It is the only reason the entire assembly holds together at all. Once the rotor could spin at those speeds without tearing itself apart, something remarkable happened to the motor's fundamental behavior. The increased rotational speed sharpened the motor's magnetic performance, allowing a far higher proportion of electrical energy to be converted directly into useful mechanical work rather than bleeding away as waste heat. The motor became dramatically more efficient. At the same time, it became dramatically more powerful. This is what collapsed the old trade-off. The reason performance and efficiency had always been at war was, at its core, a rotor speed limitation problem. Remove the limitation, and both improved together. Tesla had not simply built a better motor. It had found the door in what everyone else assumed was a solid wall. The public saw the consequences of this when the Model S Plaid was introduced. A four-door family sedan capable of reaching 60 miles per hour in under 2 seconds. That figure places it in the same acceleration bracket as purpose-built racing machinery costing vastly more money. Vehicles with no luggage space, no rear seats, and no ability to function as ordinary transportation. The Plaid carries a family and their luggage and still posts those numbers. Reviewers who had spent careers testing performance vehicles sat in the car, pressed the accelerator, and came out struggling to describe what had just happened to them. What had happened was that a physical constraint they had structured their understanding of the entire category around simply was not there anymore. For rival engineers, watching that demonstration was not exciting. It was alarming. A specification on a page can be disputed. A journalist's enthusiasm can be discounted as hype. A stopwatch cannot be argued with. The car was doing what the car was doing, and the mechanisms that made it possible were not a software trick or a favorable test condition. They were real engineering that would have to be matched in real metal. Here is where the story becomes truly difficult for competitors to absorb, because the motor is only one dimension of the challenge. Any sufficiently resourced engineering team can eventually reverse engineer a mechanism they can hold in their hands. Given time and budget, the carbon fiber rotor can be understood, analyzed, and theoretically replicated. The teardown experts who make their living doing exactly this, pulling advanced technology apart to find its weaknesses, looked at Tesla's drive unit and reached an uncomfortable conclusion. Not that it was flawless, but that the path to replicating it would take years, possibly approaching a decade, and that by the time any competitor completed that journey, Tesla would have already moved somewhere new. But the engineering itself is not even the most formidable part of the problem. The more frightening dimension is economic. Tesla has set a target for its next-generation drive systems, the complete package of motor, power electronics, and gearbox, of approximately $1,000 in manufacturing cost. Competing systems from established automakers often cost several times that figure. Some manufacturers report spending 3 to 5 times that amount to reach comparable performance levels. That gap cannot be closed by negotiating harder with component suppliers. It cannot be addressed by hiring more engineers or building a newer factory. It reflects a decade of accumulated manufacturing knowledge, process refinement, and system-level design decisions that were made with cost as a primary variable from the very beginning. Most engineering teams optimize for performance first and figure out manufacturing costs afterward. Tesla treated manufacturability as a design constraint from a start, which means the cost advantages are baked into the architecture of the technology itself rather than layered on top afterward. When a cost analyst at a legacy automaker looks at those numbers, there is no adjustment available that closes the distance. The spreadsheet does not contain a path to that outcome because the path required being Tesla, making Tesla's decisions a decade ago. To fully understand why this particular motor rattled the industry the way it did, you have to see it in context, because it did not arrive alone. It arrived as part of a system that has been assembling itself for years. Tesla's manufacturing operations span multiple continents, and each factory is treated not as a fixed production facility, but as an ongoing engineering project. The company makes its own battery cells, designs its own semiconductor chips, and writes its own software at every level of the vehicle stack. When a global shortage of semiconductors crippled automotive production worldwide, Tesla adapted faster than almost any competitor by rewriting software to function with different chips, a flexibility that required owning the entire development chain from silicon to finished product. The data advantage compounds quietly in the background. Every vehicle Tesla has delivered is contributing driving information back to the company's systems every day. Road conditions, driver behavior, edge cases, unusual events. The variety and volume of real-world data flowing into Tesla systems represents something no competitor can purchase or shortcut. A rival starting a serious data collection effort today is not simply behind. It is falling further behind every day because Tesla's existing fleet keeps accumulating experience that will never be available to anyone starting later. And then there is the charging infrastructure, which competitors initially dismissed as a convenience feature and eventually recognized as a strategic moat. The supercharger network became so reliable and so much more functional than alternatives that competing automakers made the decision to adopt Tesla's charging standard for their own vehicles. That means customers of competing brands now depend on Tesla's infrastructure to have a comfortable ownership experience. Tesla earns revenue each time a competitor's car uses its network. Its rivals, some of them century-old industrial giants, concluded that building a competitive alternative was less practical than joining Tesla's system. They ran the numbers, and the numbers said surrender. When significant competition appears in most industries, the response is predictable. Press conferences, roadmaps, promises that something better is coming soon. Noise answers noise. That is the established playbook, and it works because it reassures investors, employees, and customers that the organization has a plan. This time, the major competitors did something different. They went quiet. Not every company, and not universally. But the response from the engineering establishments of the world's largest automakers was notably subdued compared to what the announcement of a genuinely transformative technology would normally produce. The engineers who took the motor apart understood why. The silence was not modesty or strategic information management. It was the sound of expert teams realizing simultaneously that the thing in front of them did not have an easy answer. You cannot announce your way out of a physics problem. You cannot hold a press conference that changes what a carbon fiber rotor does. You cannot promise shareholders that you will have a response next quarter when the response requires building a machine that does not exist, then using it to manufacture a component that requires production tolerances the industry has never attempted, at a cost that reflects a decade of accumulated knowledge you do not have. The builders of this motor described it, by their own account, with something approaching disbelief. There has simply never been an electric motor quite like it. The people closest to it sound faintly unsettled by what they made. When the creators of a technology express that kind of quiet wonder, the competitors who have to face it have every reason to pay close attention. Tesla is not standing still. The company is working to remove rare earth materials from its motors, reducing dependence on supply chains that carry geopolitical risk and cost volatility. It is redesigning power electronics around less expensive silicon carbide components without sacrificing efficiency. Each cost reduction feeds back into pricing, which expands the market, which increases production volume, which generates more manufacturing experience, which reduces costs further. The loop accelerates on its own. The competitors who are genuinely capable of challenging at scale are few. BYD has demonstrated the ability to produce electric vehicles in enormous volumes at competitive prices and represents a real test for Tesla in markets where affordability is the primary purchase driver. But Tesla is pursuing a different objective: the most capable, most desirable electric vehicles available, manufactured cheaply enough to be broadly accessible. That specific combination, advanced and affordable at once, is what the competition cannot currently answer. The electric vehicle transition is real, and it is continuing. But the shape it is taking does not match the predictions made a decade ago about a fragmented market full of roughly equal competitors, all steadily improving. What is emerging looks more like a technology platform story. One company that solved the hard problems earlier, built the infrastructure deeper, accumulated the data longer, and structured its manufacturing costs more aggressively than the alternatives. The carbon fiber rotor is not the whole story. It is the visible part of a much larger machine. A system that keeps producing advances faster than the previous advance can be copied. That is what the engineers at competing companies were actually looking at when they went quiet. Not just a motor they could not match. Proof of a process they could not replicate.